As Max mentioned, we'll talk about source rocks and hydrocarbon generation today. And as noted in the purple box, my materials are intended for the use of students for educational purposes. So students and faculty members or teaching members of a university, college are permitted to use them. I mentioned last time that there are 2 courses that I have taught that are on the IRIS website. The first one is Geology and Geophysics in Petroleum Industry, and those have 34 lessons. And I think my next slide will show the lesson titles. And now we're on the second course on petroleum exploration, which will have a total of 8 lessons given in 6 webinars. And so the first course is more about the different components that we use, and the course that we're doing now, Petroleum Exploration, is more of a workflow-oriented set of training. So this is the 34 topics that are in that first course, G&G in Petroleum Industry. If you want more information on today's topic, lesson number 7 is on source rocks, and lesson number 10 is on seal and also hydrocarbon migration. So we won't be talking about seal today, but I will be talking about hydrocarbon migration. I showed this in our last time together, last Thursday. For an area to be economic, we need 4 essential elements: source rocks, reservoir rocks, sealing rocks, and overburden that bury the rocks and allow the hydrocarbons to mature and to percolate and get trapped. And then there's 2 main processes: trap formation and then hydrocarbon-related processes: hydrocarbon generation, migration, and accumulation. And so what we're focusing in on today are source rocks and hydrocarbon generation. The exercise, if you do exercise number 4, and I'll introduce that at the end of my prepared statement, gets into hydrocarbon migration process. So the source of oil and gas is plant and animal remains, so organic material. We need certain conditions. We need a certain amount of geological time. We need burial, and we need temperature. So the original organic material has to get transformed into oil and gas molecules. And so if we have organic material, we have the right conditions for the reactions to occur, then we get the generation of oil and or gas. With organic matter, we talk about 3 types of organic material, usually expressed with Roman numerals 1, 2, and 3. Type 1 is algal remains, and the best preservation occurs when the material is deposited in anoxic or low oxygen conditions. Type 1 typically forms in deep lakes, and they tend to generate a waxy crude oil. Type 2 organic material is planktonic and bacterial. It's in a marine setting, and again, if it's an anoxic, low oxygen environment, we have a better chance to preserve the organic material. And type 2 organic matter will produce both oil and gas. Type 3 organic matter is mostly terrestrial plant matter. It's the decomposed bacteria and fungi. Again, if it's in a suboxic condition or setting, then we have better preservation. And type 3 tends to generate primarily gas, although we can get some light oil. There are 2 source rock properties that we are very interested in. The first is total organic carbon, and people will talk about TOC for total organic carbon. That's the weight % of organic material. And so if I had 100 grams of a formation and was able to separate out the organic component from everything else, I would weigh how much that organic material weighed. And let's say out of 100 grams, I had 1 gram of organic material, that would be 1%. Anything that has 1% or greater would be considered a source rock, or a potential source rock at least. 1% to maybe 4 or 5%, it would be considered a lean source. 5 to 8 would be a good source. 8 to 12 would be a wonderful source. And the total organic content can get in excess of 15%. If we're talking about coals, which happens to be the primary source for Gippsland, that can get up to about 40%. So the more the organic material, the more volume of oil and gas it will generate if it reaches the right conditions. The second source rock property is hydrogen index, HI, and that's the density of hydrogen in the rock relative to that of water. So we're trying to differentiate hydrogen atoms total versus how much is in water. The hydrogen not in the water presumably would be in organic material. And if we have a well and we have a neutron porosity log, that particular log responds quite well to the hydrogen atoms, and so it gives us a way to measure what the hydrogen index would be given that particular log. So we need more than high total organic carbon. We need that to have the raw material, the organic matter, to start to generate oil and gas. So we're talking about a geochemical process of that transformation or conversion. And we're going to begin with the plant and animal remains, and we're going to generate molecules of oil and molecules of gas. Temperature is the primary control on this chemical reaction, and so we need to figure out what the temperature history for our potential source rocks have been in the basin that we're looking at. The temperature is controlled by the temperature gradient and also by the depth of burial. And the geochemist can model the reactions of going from the organic material to the oil and gas, and they use what is called Arrhenius equations. And so over the last 40 years, 50 years, geochemists have worked on this, and so we now are able to make pretty good predictions. If I know the TOC and the HI and the temperature history of a particular source interval, then I can get a good handle on when generation began and what volume of oil and what volume of gas has been generated. So here's a chart, here's some words. It's talking about this conversion. So we have deposition of organic material. We then go through diagenesis, where it gets compacted and the temperature rises a little bit. So in the diagram, that's the upper part. Then we get into catagenesis. That's where we have thermal degradation of the raw organic material, kerogen, and we start to generate oil and gas molecules. So in the catagenesis region, if a source rock is going to generate oil, the oil tends to get generated early with a little bit of gas. And if the source rocks get hot enough, deep enough, under enough pressure, all the oil will be generated that it's going to generate. And in the latter part of catagenesis, it will only be yielding gas. And then metagenesis is when all the hydrogen has been driven off. So in terms of looking at the geochemistry in our basin, we'll look at the stratigraphy, we'll look at the temperature history, and we'll try to figure out this diagenesis window. And commonly we talk about that being the immature part of the basin in terms of source generation. Then we have what we call the oil window, and then the gas window. And if we go beyond catagenesis to metagenesis, we call this part of the basin overmature. This is what is called a Van Krevelen diagram. On the x-axis, we have the oxygen to carbon ratio. On the y, we have hydrogen to carbon ratio. And if we plot things out, we can see the type 1 organic material up in this portion, type 2 over here, type 3 over here. And the green area is the diagenesis, and then the aqua is the, I lost the term, where the oil and gas start to get generated. So we'll generate the oil early in the thermogenic area, and then we will get gas, and then eventually we won't get anything. Everything will have been generated. So we can use basin modeling. We can use several different types of software that's available from different vendors. Some companies have their own internal basin modeling software, and we use this to try to understand the geological history of the area. This basin modeling can be one-dimensional, so we can look at a well location, or maybe what's called a pseudo-well location. Maybe we only have seismic data, but we have interpreted major horizons and have assigned them geological ages. We can model in 2 dimensions, so we can make a cross-section, maybe between several wells, or we can do 3D modeling where we'll have as input a series of grids and generate a 3-dimensional model through geologic time as to how the basin formed and filled. Our starting point, whether we have wells or we just have seismic, is the present-day stratigraphy. And then we will backstrip from present to past times. That's a process that many people refer to as geohistory. And I'll show an example here in about 2 minutes. We may have some wells from which we have temperature data. We may also have some indicators of how mature the source rock is. And so we can model the basin and try to deduce its temperature history, and then use well temperature data, and it's called Vitrinite Reflectance. I'll talk more about that in a moment. The indicators of how much the source has been cooked or how much hydrocarbon has been generated, to then try to calibrate our model. And if we can go back through time and we can calibrate it with the available calibration data, then we can turn it around. Instead of an inverse model going from present day to time of deposition, we can model it forward through time, from time of deposition to present day. And we can look at the source and try to understand generation and how much oil volume and how much gas volume was generated. And we can do the same thing with reservoir. What was its porosity and permeability at the time of deposition, and with our software, see if we get to present day porosities and permeabilities. So I'll use as an example backstripping of a well. So we have well A. We know what the present day stratigraphy is, and so we have a depth below present day sea level, and then we have the formations color coded, and the numbers on the far right are the ages in geological time. We have some seawater, the light blue, and then we have no deposition from 0 to 30 million years, and then we have a formation, the tan from 30 to 70, the orange from 70 to 110, and so on and so on and so on. So the software will allow us to backstep by removing one layer at a time and trying to reconstruct what this 1D location looked like through its geological history. We'll datum each of our steps back either on present day sea level, or if you have a preferred sea level curve, such as the Hawk sea level curve, you can datum it using that. We do need an estimate of paleo depths, and we also need the geological ages, and oftentimes we'll have micropaleo from the wells that will give us both ages and approximate water depths. So this method will allow us to model how the basin has subsided and then filled with sediment. The software will decompact the sediments as we go back through geological time. I don't have decompaction on the diagrams that you're about to see. So here's well A, present day stratigraphy. Here's the depth from 0 down to 7 kilometers. So we can fill out the geological time. So we're going to start 200 million years ago in early Cretaceous and look at the history up to present day. And we start by going backwards in time, starting present day and going back. We can put in either a constant sea level or a varying sea level. And then the light blue is meant to represent the water column. We would get paleobathymetry from our microfossil data. And then we just start stripping off one layer after another after another. And I don't have decompaction in here, but the software that is available will include that. And so now I can look at total subsidence from the oldest rocks that I'm interested in, or maybe the deepest rocks that the well penetrated. And I can see how over time it has followed this particular path to get from near sea level down to looks like 6,700 meters. And then I can look at, for each of the individual formations or units or sequences, how that burial has occurred. Now, if, as an example, this, I'll call it jade. If this jade formation is my source interval, I can see how that has gotten buried from the time of deposition to present day. And I would also like to try to deduce what that thermal history has been. And given that, our geochemists can then calculate how much hydrocarbon has been generated and the history of that generation of oil and generation of gas. So if we are in a divergent, pull-apart Atlantic type of margin, we can do some extra things with the geohistory. Here is the total subsidence in red. Here's the sea floor in the darker blue. And this total subsidence is due to two main factors. One is the weight of the sediment, and the other is the tectonic and thermal forces that have been applied to this particular location. So if we have an extensional pull-apart type of model, this isn't the most current type of model for rift basins, but we start with continental crust on the order of 35 kilometers, and we're going to extend that down to about 10 kilometers, and then have oceanic crust and perhaps a mid-ocean ridge. You can also see how the mantle thins down and the asthenosphere gets closer to the surface. And so all of this extension and rifting causes heat to escape from the asthenosphere and the mantle and impact the crust and what we're interested in, the sediments. So for this model, we can consider crustal extension going from 0 extension out to 100% extension, where we have the continent-ocean boundary. Now, Royden and her co-authors back in 1980 did some theoretical work, and they came up with a series of subsidence curves for different degrees of continental stretching. So this does not include any sediment weight on top of it. The 1 or 100% stretching, that's derived from the actual seafloor topography from a mid-ocean ridge out into older and older crust. And so the way we can read this is that, let's say, for example, this 0.4, this would be the type of thermal substance we would expect if the crust at the location we're looking at was extended 40%. And down here would be 70% and 90% and 100%. So if I go back to the well A that I've been looking at, I can figure out, given this stack of sediments, what the weight component of subsidence is, and that's what's shown in tan. And so this magenta line would be the what the crust would have done if there was no sediment load put on top of it. And so then I can take the Royden curves and superimpose that, and that looks like a reasonable match. And if I had a better memory, I would remember what the percentage is. I'll look at that in a minute. Ah, there it is, 70%. So I would say the time of when the thermal subsidence, the sag phase started, would be in the latest early Jurassic, and that at this location, the subsidence is telling me that it was probably extended about 70%. With that information, then I can determine what sort of background heat flow the area might have had and how much extra heat is associated with a 70% crustal thinning that ended in the early Jurassic. And so in purple, that would be the heat that is associated with that rifting event and how that heat dissipates as time after rifting increases and increases. And so given that heating history, I can then model the temperature for any of the particular beds that I'm interested in. And for our purposes, we're most interested in the temperature history of the primary source and if we have any secondary sources. As I mentioned, we can do some calibration here if we have some temperature data from the wells. And so for this well, we have 1, 2, 3, 4, 5, 6, 7 temperature measurements as a function of depth. We can see how the computer model predicts the temperature profile. And this looks like I've iterated a couple of times trying to figure out what sort of background heat flow and what sort of stretching factor was appropriate. But this is a reasonably good fit to the present day temperature data. The other thing I can look at is what's called Vitrinite Reflectance. The organic material is looked at by people under a microscope. They look at how shiny the vitrinite particles, you can kind of think maybe of coal as an example, how shiny a piece of coal might be. That has a scale that the people that specializes in these measurements know, and these can form paleothermometers. And so again, I can look at the present day stratigraphy. I can use the temperature history that the software has developed for me. And now I have 1, 2, 3, 4, 5, 6 data points where from the well data, someone has looked at the organic material and figured out the vitrinite reflectance values. And you can see my scale goes from 0.3 to 1.3. And so again, I can see, does the model predictions of vitrinite reflectance, which is designated R sub 0 or RO, how well those data values fit. There's less precision in RO numbers, so a bit more scatter is acceptable. These RO values are important because I know from past experience that the top of the oil window is at about 0.55 RO, and the base of the oil, top of the gas window, is about 0.95. And so given this model and these values, I can then say the top of the oil window looks like it might be at about 3,350 meters, and the top of the gas window looks like it's at 5,600 meters. So what we'll do is we'll look at the available data and try to identify intervals that could be potential source rocks that have a good total organic carbon and hydrogen index values. We can collect TOC, HI, temperature, and vitrinite reflectance data in and around our area of interest so that we can calibrate our models and then calculate how much hydrocarbons should be generated. We can select locations to do this geohistory or basin modeling, look at the subsidence and the fill, hopefully develop reliable temperature histories. We can use actual well locations. We could use outcrop locations if that was important. And we can use locations where we have seismic data and we have interpreted horizons that have been given geological ages. So we call those pseudo-well locations. We'll make initial runs on our models and we'll see how well the temperature and RO data calibrate to our models. And so we may do some iterations until we get a better tie between the modeled temperature and the recorded temperature, the modeled RO and the recorded or observed RO. And we also might want to do this throughout our area at a number of points and make sure that everything looks aerially consistent. We would then develop a depth versus RO relationship, and that's what I showed on the previous slide. And then we could say that the top of our oil window is at a certain depth, the top of our gas window is a certain depth, and the base of our gas window, the start of the overmature region, would be at a third depth. And then we can use these relationships and depth maps to then be able to put on a map view where, at least present day, the oil generation window is and the gas generation window is. If I can reconstruct the depths of the source rocks for earlier periods of geological time, I can see how the oil window and the gas window have changed as I go from, let's say, the Oligocene to the Miocene to the Pliocene to the Pleistocene to the recent. So I will stop there for a few moments and see if there are any questions. You can use the chat portion of the GoToWebinar control panel to type in a question. Max would read that to me, and then I would try to answer that. After a couple of minutes, then I'll talk more specific about source rock analysis in the Gippsland Basin and introduce you to the exercise which you may or may not want to complete. So Max, if there are questions, let me know.
Yeah, so there's one question so far. Alonzo is asking, might there be any problems if there is a large igneous body near your source rock? And he gives the example of off-coast Peru.
Yes, there are complications that I don't have time to get into. One is igneous bodies, so that's a very good observation and question. Another problem that we face is that if we have salt features, salt conducts heat differently than sediments, and so sometimes we can get hotter and cooler spots depending on whether we're close to a salt diapir or further away from it. Another thing that gives white hair to people that do this is if we have missing section. How much rock was there and how much was eroded away, and so that can affect the burial history. We also have to worry if there's been regional uplift. So what was the maximum depth of burial? What was the maximum heating before maybe the area being raised up? So there are a number of complications, and the simplest basins are the extensional pull apart, where we have a good model as to what sort of heat flow we should have. We have more trouble working with compressional basins and with strike slip basins. Excellent question.
Those are all the questions so far.
Okay, so let me introduce exercise 4. Even if you don't do it, I think it's worth listening to me for another 5 minutes or so. If you do the exercise, what you would be given is a 1D source generation model, and then you will be asked to figure out where is the oil window present day, where is the gas window present day. Consider how much oil might be generated for the Barracuda prospect within its fetch area, and how much gas would be generated. And so the final product of the exercise would be an estimate of the volume of oil generated, the volume of gas generated, and then we'll make an assumption in the exercise that 90% of the generated hydrocarbon actually makes it into the trap. So our regional analysis for the Gippsland area suggests that the Golden Beach Formation is the primary source. Its geochemical properties are available to us from some outcrops of the Golden Beach, and we have, I think, 20 onshore wells, and some of those wells have penetrated the Golden Beach, and we have some samples of the source rock. Based on the organic matter type, which is largely terrestrial, we expect that the source will generate a little bit of oil, but a lot of gas. And so one of the things that we're already thinking about at this point is that we don't have a good oil generating source, and so we should be thinking about gas fields, maybe with some oil, rather than oil only. For the blocks that we have, our company has license for, we would do something like 12 locations, and so the dark red dots are where, hypothetically, I would run my geohistory analysis. I'd look at the amount of crustal stretching. I would try to come up with a heat flow model for each of the 12 sites, and then look at how that is distributed over this particular area and see if it makes sense. So the axis of the basin would be to the southeast. The unextended crust would be much further to the northwest. And so if, let's say, this location had 50% stretching, then I think this one might have 55 or 60. I wouldn't expect this to have 30% or 20% stretching. And so that's the aerial consistency that I mentioned. So we do have an extensional basin, so we can use Royden et al. Theoretical work to try to come up with the temperature histories. And we boil that down to a diagram of source maturity. This could be vitrinite reflectance up here, and then depth in meters. And so for our source interval, 0.55 R0 comes in at a depth of 1930 meters. So we start to generate the oil that the source will generate down to 2,500 meters. Then from 2,500 to 3,160 meters, we would only be generating gas. And if our source gets deeper than 3,160 meters, we would be in the over-mature, so we wouldn't be generating oil or gas. Our model will also tell us what percentage of the organic material volumetrically would convert into oil and into gas. So what we have and what we need, we have source maturity, and generation is a function of depth based on our geochemical models at 12 different locations. And if you've been working at the exercises, we have a two-way time structure map for the top of the reservoir. So what we need is we need to know where at the present day is our oil window and our gas window around the Barracuda anticline, which is our trap. And so if we could get a map to the top of the source in meters, then we can use that model and those depths to indicate where the oil window and the gas window would be. So how do we get from where we are to what we need? A solution, if we can relate the depth of the source to the depth of the top of Latrobe unconformity, which we have time map for, that would be the first step. And perhaps we could assume that there's a constant thickness between the top of the Latrobe and the top of the source. If then we can convert the top of the Latrobe depths to an equivalent two-way travel time, and that's what units our maps are in, then we can say that the top of the oil window is at a certain number of milliseconds, the top of the gas window is deeper at another specific two-way travel time. Then we can map out where our oil window and where our gas window present day are. So without getting too bogged down into the details of the exercise, let me stop there. And again, there may be some questions on what I covered today, either in the lecture, or maybe you're curious about something related to the exercise. or maybe you have a lingering question from lecture 1, 2, or 3.
Nothing so far, Fred.
Okay. So Thursday of this week, February 1st, 1 month already gone, we'll have our 4th webinar, and that will be on lecture number 5. We'll talk about the reservoir rocks. So in the absence of any other questions, I will wish everyone a fantastic rest of the day, and look forward to seeing you again on Thursday.
Thank you, Fred, and we'll see you for the next webinar.
Okay, thank you, Max. Have a great couple of days until we talk again.
You too, Fred.
Bye-bye.